All right, so for linear regression, it's the first model that we're going to cover within supervised learning models that come from labeled data. It's a statistical model that predicts a continuous target variable, okay, using a linear relationship with, input features. Yes. Polynomial regression, ridge regression, lossy regression, elastic net regression, they are going to be like an extension, right, of this linear regression that we will cover. So polynomial would be to model nonlinear relationship by using polynomial terms, right? As you might imagine, as you might guess from your math knowledge. So ridge regression is basically, we're gonna use some regularization parameters like L1, L2. I believe in AI course, you should have mentioned those terms. Basically, those are to prevent, you know what it is for? Yes, good. It's for preventing overfitting by, penalizing like large coefficients and so on. Lossy regression, also, it's a linear regression model with L1 regularization. It's promoting sparsity by reducing some coefficients to 0. So, and elastic net is basically a combination of ridge and lossy. So it balances L1 and L2 regularization. So for classification models, we're gonna go with some of these guys like logistic regression and so on. So logistic regression basically for classification, binary classification that estimates probabilities using the sigmoid function that we will see. Decision tree that splits data into branches based on feature values to make predictions, right? Random forest is gonna be building like multiple decision trees, and it averages their outputs for better accuracy, I would say. Support vector machines or SVMs, they find an optimal hyperplane to separate data, right, into different classes. K nearest neighbors, right? That's different from k-means, so don't get confused. That was for unsupervised. K nearest neighbors is a non-parametric, that's also a classification algorithm that assigns labels based on the majority class of the nearest neighbors. So K, that's coming like to assign the nearest naive Bayes is like a probabilistic classifier based on Bayes theorem, and so on. See, there is going to be a much more advanced high performance methods such as GBM, XGBoost, and so on, and the neural networks, basically that you use in deep learning. So we're not gonna get too much in detail for unsupervised learning for now, but I'm just letting you know what types of models are within unsupervised learning, which comes from unlabeled data. So now you remember, I guess, right? We covered k-means clustering, one of the clustering models. You could do clustering, you could do dimensionality reduction models. After we're done with, supervised learning models, we're gonna cover some of these as well. Like k-means we already covered. We're gonna cover PCA, which is very important for dimensionality reduction models. And there are some association rule learning algorithms, and there are some anomaly detection models. Autoencoders are very common in doing so. It's also a type of neural network, actually, that is covered in deep learning. Yes, so So, you know, this is just an example for a machine learning task, like a template you can reference from. So you're going to have training data like labeled as you see. Let's say these ones are pink ones are spam and the yellow ones are request. So you train a model, right? You put this data, this training data into the model, and the model, you're training the model, by the way, and the model learns from the labels, from the features, and then it gives you, with the test data, it gives you a requested class. Yes, so you're going to have like spam um, labeling in this case. So guys, we're going to split the data set for training testing, as I mentioned earlier. Usually it's for the training data. Let's say you have 1,000 data in your data set. So usually 700 or 750 is gonna be your training data, and the remaining will be testing data. Okay, so, and I'm sure you covered these terms. Basically, you're gonna have like a concept called epoch when it comes to deep learning. So the epoch is like a time period marked by feeding the whole of your training data set to the model. So you'll need to repeat this process, right? To start seeing at least half decent results from your algorithm. So epochs are helping you determine if your model is learning from the data. And if it's learning, you're going to have a process, a chart looking like the one in the middle. So if you don't repeat this process enough, you'll face a phenomenon known as underfitting on the left-hand side, which is basically a low accuracy of your machine learning predictions. If you overtrain your model, you'll fall victim basically to overfitting, which will, you know, as you see, lead to the poor ability to make predictions, you know. So that's also not good either. So you gotta be careful with underfitting, overfitting, and there are some solutions that we will see along the way. So now today we're gonna start with supervised, with a supervised machine learning algorithm, which is linear regression. So basically, it's an approach for modeling the relationship between two variables. So the dependent variable we will call y, let's say, that's the dependent variable, is the quantity we would like to predict, right? For example, the rental price. And we predict the dependent variable using the known value, right, of the independent variable, x. Predicting y using x. So guys, there are so many x's, right? That in the x-axis, right? And corresponding y values. So I'm sure from math, you know how to find like a correlation between these. And the formula to do so is y is equal to a plus bx. So what is a and b? Do you remember? What are those parameters? That's the thing that you're finding out with the linear regression. You're finding those a and b's. So you create a model. Hey, y is a value plus a value multiplied by x. So do you remember what those values, the name of those values? What is b in this? Yes? Yes, that's the slope. Good job. That's the slope, right? So guys, this is the data. And the idea is to find a linear line, right? Like a straight line, basically, that refers to a linear model, like a projection, right, of this data. So the slope of this line is basically b, but you have a fixed value too. What is that called? It's called intercept. Yes. And each data here is basically x, y values, right? You put it in parentheses, right? x20 for, let's say, 8, I don't know, something like that. So in parentheses, 20, comma 8. That's like 8 is the value for correspond for x. So x, y, 20, sorry. So basically what we are doing here, a simple linear regression finds the line, right, through the points that best fits the data, right? So yes, how do we do that? To determine the line of best fit, like how do we determine, have we found this line, but if it's the best fit or not? We use some metrics, right? We're gonna see. One of them is the method of least squares, MSE. The method of least squares. I'm gonna give you the formula for that. Basically, you're finding coefficients A and B, right? Here. So, giving that concept, so we have a problem, we have an example, what we're trying to find, the model, and so on. What are the steps that we should follow for this linear regression concept? We're gonna have some data. So go to the modules in web courses. As always, download the data from the same directory as your Jupyter notebook that you will create in a second. So download that data, company data CSV file on web courses week 7. After downloading that data in the same directory as your notebook, we're going to read and understand that data, right? We're going to visualize it. Let's like how it's looking. And then we're going to start our model problem. So we're going to split the data into training and testing. And then we're going to perform linear regression, right? For the model to learn from the training data. And then we're going to do predictions on the test set. And then we're going to evaluate the model. So these 6 steps. Cool. So that's for linear regression. And again, this is like, guys, this is what kind of output do we have here? Are we doing classification here? No, right? Remember we had 2 types. So this is a regression model, right? It's a continuous value. We are predicting continuous values, like house prices, as I told you earlier. But, so we're gonna implement this, but I want to mention another method called logistic regression, which will give you a constant output. So it will give you a class, it will give you a category to predict, let's say, if a patient has, sickness or not. Okay. So basically, linear regression that we will see in a few gives you continuous output. House prices, stock prices, and logistic regression gives you a constant output, like a class, like binary classification, right? If the stocks will go up or down, that's also considered in that category. So linear regression is estimated basically using ordinary least squares. And logistic regression is estimated using maximum likelihood estimation. So we're gonna see those terms. Basically, MLE here is a likelihood maximization method. OLS here is distance minimizing of approximation method. Makes sense because we're finding like a line in this category, right? So maximizing the likelihood determines the parameters that are most likely to produce the observed data. So MLE in this case sets the mean and variance as parameters. Yes, in determining like specific parametric values for a given model. And here, OLS, the estimates, OLS estimates are computed by fitting a regression line, right, on given data points. That has the least square error, right? We're gonna see that too, sum of the square deviations. So so you see like an S shape in the logistic regression. That's also called, so that's like sigmoid function, also called logistic function, that can take any real valued number and map it into a value between 0 and 1. So if the curve goes to positive infinity, y predicted will be 1. If it goes to negative infinity, y predicted will become 0. Okay, so those are just differences I just wanted to give you here before we start implementing for those two. So we're gonna start implementing the linear regression first, covering all those what I said here, and then logistic regression here. So start a new notebook, select your kernel, rename it linear regression, enter. Okay. So guys, the thing is we're going to, of course, try to understand the data, right? Company data CSV. So as always, we're going to import numpy as np, import pandas as pd, right? Run it. And when it comes to machine learning and stuff, if you don't want to, sometimes like we take a lot of warnings because of the data, how it's created. You could suppress those warnings, guys. So if you don't want to see them, this is optional. So import warnings, warnings.filter. Comes with this method, filter warnings, and fit it, ignore, so you won't be able to see those. Now let's start reading the CSV file and then view some sample records, right? And company data, so let's call it advertising, and you will see why I am calling this advertising, by the way. pd.read CSV, right? um, company data dot CSV. And let me see this. So you see, I call it advertising because I see some sales option, TV, radio, newspaper, sales, and I called it advertising. What does this give you about the data? What kind of information you can extract from this data, or what can we analyze on this data? Perfect. Good job. That's exactly what it is. Nice. So basically, which one of these tools will impact, like, maybe the best for the sales, right? So sales is our target value, right? It's our Y. So we have to predict that using, one of these and see each of these actually and see which one is like has the most correlation, I would say. Does it make sense, the problem now? So guys, you always have to, when you start, you look at the data and you find a problem and you define your problem and then, find out the solution accordingly. So what can I do next? We said our target variable is the sales column. Yes, so basically we see TV, radio, newspaper there, and the values are like the amount spent on TV advertising, right? Amount spent on radio advertising would be like in dollars or something. And the total sales corresponding in the same row. Yes. So let's understand, and you already see like how many data is in this data set, 200, right? There's 200 data. Okay, we know that for now. You could also know it with another like shape. That's one of the methods that you will use a lot. Okay. And the other one, another one to check out information about data. Info. Okay. Founded entries. And there is one more. Yes. So here, guys, you see a bunch of statistical calculations, right? And count already, like how many of them, it's easy. Mean, the average values, standard deviation, minimum, percentile. Those are like how many of the values are less than the given percentile, right? 25, 50, 75, and there is a maximum. Yes, so you could use those information. So we have some idea about this data now. And if you want to have like more ideas, like to have like prior information or prior correlation, you could do some visualizations about this. Since you already determined the target variable, which is sales, you could visualize the, how it looks like scatter we did, like TV and sales, newspaper and sales. So plot those and see beforehand, like, okay, let me see visually like how they relate before I get into the programming, modeling, or finding a linear model. So you could have some idea using visualization, um, like to decide, okay, which advertising tool should I go with? I know that my Y, you know how we had Y is A plus B X, my Y is sales. So I want to determine what is my X, like to see which one fits, has the most correlation, the best correlation. So you could do it by visualizing also. And let's import those visualization libraries. Which ones have we seen so far? Visualization, matplotlib, and SPLT. And we had seen another one, Seaborn as assets. So the best tool would be to see those correlations would be scatter, guys. So, and you remember you could use pair plot. Advertising, that's what we named our data frame, right? X variables. Now my X variables, I'm defining them here. You remember you could define multiple X variables and see multiple subplots and pick which one has the best correlation basically. So TV, radio, newspaper. And so I define my data frame, X variables, Y variables, just sales. Just sales. These are just some other parameters, some optional, and kind, I want to pick scatter. All right, now, and lastly, to see what am I using? Show. Okay, so you see, let me zoom out for a little bit. Guys, what do you see? What can you tell from this plots? So you see, we only have one Y, sales, and we have TV, radio, and newspaper. So which one do you think we could have like a best like linear regression model on? TV, right? Yes. So because they tend to create a line diagonal, right? And the others are more like spread through the graph. So let's see. Okay. So and remember when we use heat map, we also show the values, correlation values on each cell. Do you remember that property that heat map comes with? Okay. I'm sure you will remember when so let's do the heat map. Um, so we want to find the correlation, CMAP. There is this value that you can assign for CMAP, guys. You know, that's like coloring map. E, Y, L, G, and B, U. Okay. Annotation is true. So basically, this guy here, it's a sequential, you're gonna see like a sequential plotting, like it uses colors that progress from low to high, right? You will see it. And lastly, to see this, you're gonna do close as always, but show. All right, you see the values I told you. The annotation true is going to give you. So diagonal, we have ones, right? Because TV and TV, of course, correlated as one. So the higher, the, more correlated. As you see, TV and sales is the highest among the others with the sales. So radio and sales, very little correlation. Newspaper is the lowest, right? Newspaper and sales, 0.60, the lowest one. And yeah, so you see some diagonal properties equal here. So pay attention to those two, of course. That comes from having the same attributes in x-axis and y-axis, of course. All right. Now we go with the TV and sales, right? Now we made our decision to perform the linear regression. Yes, so the correlation between TV and sales is 0.9, 90%, or we would say. So that's like a strong relationship. So guys, again, as always, we're gonna create, what is our first step? Create the X and Y, right? So you're going to basically assign future variable TV as X, target variable sales as Y. So the independent variables represent X, that's the TV, and Y represents the target variable. In our case, remember this linear regression equation. So what is our equation here now? What is our equation? Y, so that's sales, intercept, slope, multiplied by TV. Okay. So with that being said, let's get started. So let's create the X and Y. So X is the capital X, by the way, is advertising. That's our data frame. And it has the TV column, right? TV column. And Y is the advertising sales. We define those. Next, okay, what is next? We're going to, guys, split the variables as training and testing, right? That's what I told you. Okay, for that, guys, sklearn library. So we're gonna use sklearn for machine learning tasks, right? So we used a lot of libraries so far for data analysis, data manipulation, and so on. And for machine learning, we're gonna use sklearn. So if you go to here, as always, Google it, you'll find this website, sklearn.org. And as you see, you're gonna see like the task that I told you, like clustering for unsupervised learning, classification supervised, regression supervised learning, all those algorithms, guys, all, with examples, with coding and everything. That's like great tool for you also to practice. Okay. And yeah, so you see there's dimensionality reduction. We mentioned we're gonna see PCA and some pre-processing that prepares your data before you even train your data. There are some methods for that too. So this is the website. Okay, so I said we're gonna use scikit-learn for machine learning purposes tasks. So we said test, train, split data, right? So scikit-learn has that method built in already. So we can just import that. So from scikit-learn dot model selection. This model selection has train, test, split. Of course, later on, we're gonna feed parameters that determines like how much of the data is trained, how much of the data is test. It's coming up now. So, and with this, guys, we're gonna have, so we have test set, train set. Then how many variables am I having now? So I had initially 2, X and Y. Now I have 4. Let's name those. So X train, X test, Y train, Y test is gonna be coming with from this train test split, guys, here. Okay, it automatically assigns those values in this order: X train, X test, Y train, Y test. So this, the output of this method, when you feed into the parameters that it requires, right? This part, the right side of the equation. The output of that method is giving you 4 values already, right? In order: X train, X test, Y train, Y test. So keep that in mind. And I'm feeding this all the X's and Y's, right? All the X's and Y's that I have for TV and sales, right? And I determine the train size. That's the parameter it has, train size. And I want like 70% of it. So I put 0.7. I said test size. And random state, guys, this is for, whenever you start over, you can just put any number, 16, doesn't matter. I think we talked about this before. Random state is like whenever you, since this is randomly selected, guys, this train test split, splitting the data is randomly selected. Each time you will run this code, will generate new data. So you will see all different results. The results might be closer to, of course, the values, but the data will be selected randomly, so it will be different. In order to prevent that, meaning in order to have the same data whenever you run this code again, you assign random state. Done. Next, let's have a look at dot shape, let's say. How much should it be? 70% of 200. 140, right? 140. Cool. Test. 60. So 200. Perfect. Now, guys, when we do here's another concept that you need to know. So this is only one-dimensional data, 60, 140. But in order to train a model, you need two-dimensional. At least the machine learning models here requires you to have the input data in 2D array format. So, because scikit-learn models expect 2D arrays. In order to do that, you're going to add additional column to the train and test set. So let's update our input data. So which function does that? So this was our initial values, right? So I'm reshaping them. This is just a convention to have a two-dimensional data. So let me update this so it should look good. Okay. Now let me see X train. Shape, right? Okay, let me see the X train shape first. Yes, now it's a two-dimensional array, and then the X test should be also two-dimensional. Yes. All right. Now we can proceed. So we basically fitting the line. We fit the line to the plot, right? Importing the linear regression model. So how do we do that? Scikit-learn has a built-in linear regression model. The concept that I just described you don't need to write it from scratch. You can use it from scikit-learn, guys. So from, again, of course, you could import these at the very beginning, but I'm just showing you them once we get to use them along the way. Usually, how this works is we want the time that we need a method, we go update the importing section right here. We just add it up here, everything. All the libraries we add at the very beginning, but for teaching purposes, we could also call them along the way. So linear model, that's what it is. So linear model, so scikit-learn has linear models. And from there, we're gonna import which one? Linear regression. It has a bunch of them, right? You can have a look. You can just see what others does it have. So from here, since this is a class, let's create an object. Like, so we could use this object with its corresponding methods. So we can provide the parameters, X train, Y train, Call it LRM, linear regression model. Okay, just LM. LM is linear, doesn't matter, linear regression. Okay. So these steps are important. So we import the model, we create an object of that model, and next we fit the model. So LM fit. So we basically, fit is the method that trains using that model, trains the data. So what does it need now? The data. The X values and its corresponding Y values, guys. So as you see, with the supervised learning, we know the labels, we know X and we know the Y, we know the corresponding values. And we're just finding the slope and intercept to get the equation of the model, right? Basically creating the model using this. So if you run this, what's that you're going to see? Okay, now it ran successfully, so it's creating the linear regression model with your data. Now, what would you do next? Basically finding the coefficients of the model, right? What are those coefficients? Intercept and slope. And again, this linear regression has a built-in method that just gives you the intercept and slope values, because it's already found it. It's there. We fit as soon as you type the fit, it's finding it for you. Your model is created. So let's find it out then. You're just gonna write LM intercept underscore. So 6.86 and so on. It's your intercept. Which one is this based on what I wrote here? It's the C, right? Okay. And the slope, same, similar, LM dot OF. That should give you the slope. Yeah. Okay, so this is your M, the slope. Now, then what is the equation? Put it into equation now. Sales is going to be 6, let me see. What was our equation? Just let me get it from here. Okay, now sales 6.86, right? Plus the slope is 0.0, oops, 5, let's say, multiply by TV. Yes, so you found your model. So this means, like, let's say for every $1,000 increase in TV advertising spending, sales are expected to be increased by 50, 6 units. So, and the intercept 6.86 is basically the estimated sales when TV advertising spend is like $0, right? When it's 0, when it's 1, that's when it's increasing. All right, so from here, we can evaluate this. Okay, so how do we evaluate this? So, with the, so we train the data with the training set. So what about the testing set? We haven't used them. So we're gonna make predictions using this model, this equation, and check if, we're gonna give those X values in the testing set, and we already have the correct values for those X's, right? So we have correct, true ground truth, we say. We have the true values for those X's in the test set. We have X and corresponding Y values. But we found a model. So the X values in the test set, we feed into in here, and we find a Y predicted here, right? So meaning that, so what I say here is basically, we found the slope and intercept using the training set. Now we have the equation, right? So next you could get the X values from test set and find its predicted Y value, and basically compare it with its actual value, right? Do you see what I mean? Because you already have the actual values in the test set for those X's. So that's like idea here. Like, and then you evaluate, okay, what is my error rate, right? So how good is the model that I found here? So this is the idea of machine learning, linear regression here. So there is a R squared, which is a statistical measure, and there is also mean square error, guys. You could use, usually mean square error is the one that is used widely, but here, see, I found an equation, and let me should be this. Okay. Evaluations. So I can just, I should be able to put it. What is this thing like? All right, then this is just an image. You could just drag it and put and run this cell. It has to be marked down. So you see. So basically, okay. Take a look at these two evaluation metrics, R squared, MSE. So we imported the required metric, which is called R2 underscore score. Okay, and then we're finding the prediction prediction values for Y values in the training set, and the prediction Y values in the test set. Now, since we have Y train and Y test actual values also, now we're gonna we're gonna use R square score to compare and to find the value, R square value. You know, the higher the better, meaning it's gonna be the closer to 1 is better. So R train, meaning R square on train, is R2 score on which values? Y train and Y train predict, right? The actual values and the predicted values on train set. R test, R2 score, Y test, that's the actual values, and this is the predicted values. Now, compute those. Let's see the R train. 0.81, that's not bad. And R test, that's like 81%, right? Not bad. R test, 79%. Okay. So our model is learning in that rate. Another evaluation metric we said mean squared error, right? It measures the average of error squares if you want to look at the given formula here. So meaning that the average square difference between the estimated values, right? Estimated values and true values. So and let's evaluate our model with this metric. So learn that matrix import mean error. Call it MSE and use this method with on test data. So Y test and Y test red. Cool. And just print it. So this one should be close to 0 because you don't want to have any error. So the 4 is not bad here. And for visualization, guys, let's see. Let's draw the line, right? We never did that, I think. Did we? No. Let's draw the line here. That's the one that we just found. Yes, so this is the actual data. Let's fit the line in this data. So let's do it as our last step. Scatter X test Y test. So that's like our actual data scattering, right? Not predicted values. Now, in order to draw the line, we're gonna use what? In the same plot. Which parameters I'm feeding here? And I have the predictions, right? So predictions, that makes it the line. There we go. So that finalizes our example for linear regression. Okay, now we have a good background in this model type, linear regression in supervised learning. Okay, so now next thing that I want to discuss is logistic regression. Hmm? Um, we can, yeah, but along the way, the more models we see, we will talk about those too. There is going to be regularization, normalization, a lot of concepts in machine learning. So we'll see along the way. Um, so again, linear regression is giving us a continuous output, right? But logistic regression that we will see now, it will provide us a constant output, right? Like classification, 1 or 0. So let's go and open a new notebook. Name it um, logistic regression. Logistic regression, yes. Okay. So here, guys, we're gonna have another. We're gonna have another file. So another data set. So let me add it here. So go to week 7 again. You will see diabetes CSV file for, let's use it for logistic regression. And you'll see why we are using this once we go through the data set. Again, actually, copy paste this. Okay. And then pandas, we're gonna read it with pandas, right? I just wanna go through the data, the diabetes. See how it looks. As always, that's our first step. So let's call the data frame schema pd dot read csv diabetes dot csv, and then let me see the first 5 records. So you see there's a bunch of columns. Oh, what do you see at the end? The final column that you see. Outcome. What does that mean? If the person has diabetes or not. If it does, if they do 1, they don't 0. So that's logistic regression. And it's like classification, see? So it's different from linear regression that we did. So now, guys, and you can have the idea now what we're gonna do, right? So we're gonna have, again, training set, test set. We're gonna find a model from the training set. For test set, we're going to predict the corresponding outcome, and then we already have the ground truth for those, and then we compare if our model is doing good or not with the evaluation metrics. So same idea, similar idea, but a different task here, right? So, okay, let's get started now. Let's see how many data we have. Pima dot shape. 768, there are 9 columns. 8, 9 columns. And the last one is, basically the last one is our outcome given. See, this is a labeled data also. You know, in most, especially healthcare or financial data, you might not have this data. So that's unlabeled, then you're gonna use unsupervised learning. So this is labeled. Okay, sometimes the data they give you is not enough. Then you might need to use semi-supervised learning. So some of the data is labels, and some of them won't. So those are the things. All right. Now, you can also do some feature here. Guys, there is this concept called feature selection, actually. So each column that you see here, that is a feature that affects a person to be diabetes, or not, right? So, and maybe some of them won't really affect in these features, but let's pick for simplicity just some of them. So feature columns. And glucose, I want to pick. It's skin thickness. No, I want to pick insulin. What else? Okay, BMI. What else? All right, I'll pick most of it actually. And H. All right, so here my axis, right? Again, we define the x's and y's. So my x will be Pima, the features, right? That's your features. And y would be the target variable. That's the outcome, right? That's the outcome, this guy. It's our target. And the next step again, guys, splitting the data. Okay, so what did we use when we did splitting the data? Same idea. We can just go so this is just visualization. Here, you guys, here. So take this line, this cell, basically, bring it here. Let's see. Okay, from scikit-learn model selection, import that, blah, blah, x train, x test, y train, y test. X, y trains. Okay, let's update this. You don't have to, sometimes if you just define the test size, the train size would be automatically assigned. So make this 25, that should be fine too. And random state. Okay, this is my parameters this time. All right, now I want to see X train shape. How many? Five. Yes, 5, 7 is 6 and 7. Yes, perfect. So I picked 7 features and 576 data in the training, and the remaining 192, I guess. Let me see. In test data, let's see how many. 192. And from here, so far so good. Now I'm going to use, guys, the model, right? So we're gonna do model development, and then we're gonna do prediction, and then evaluation. Yes, so now you know the steps. So, you know, we imported the linear regression earlier. Now we're gonna import from scikit-learn. It's a linear model again. We're going to import logistic regression this time. And again, guys, instantiate the model, the object. Let's call it this time logreg. Within this class, you can also set random state. You know what it is used for. And next, we're gonna fit the model. Yes, so logreg dot fits x train, right? Y train. Cool. Now the model is found, by the way. So let's see what we have done next here. We have done fitting, and we found the corresponding model coefficients. But here, what do we find? Prediction, right? Here, we're gonna find only the predicted values. Yes. Okay, so now how do you find the predicted values from the test set? So y prediction log reg dot predict, guys, test set. So you know X test has the corresponding actual Y test values, but I'm finding the prediction so I can compare. Okay, run this. Now Y prediction values are found for those X test values. But for X test, I also have Y test, right? Where is it? See, Y test. These are the actual values. These are the predicted. Now we have to compare them and see how accurate. You know, this is gonna be like 1 or 0, 1 or 0, and 1 or 0. So we compare which one, how many of them are correct. So 192, right? Out of 192 data, how many do you have correct labels when you predicted? That's our next step. All right, when it comes to binary classification like this, right? 1 or 0 binary classification. We use confusion matrix, guys. Confusion matrix. Okay. So basically it's to evaluate the performance of a binary classification model, and each cell in the matrix represents a count of predicted and actual values. Count of predicted actual values. And this is how it looks like. I said each cell. So it's 2 by 2. You're going to see a 2 by 2 matrix. Confusion matrix is a 2 by 2 matrix. And each, so there are 4 values. Each value is a count of predicted values. And let me show you here, CM confusion matrix, put here. Can't do it that way. So it's here. With the CM, I'm gonna share all of this with you. So run this. So guys, here you can have a better idea. So there are gonna be, what are those? See, there's gonna be like 4 values: true positive, false negative, false positive, true negative. True positive and true negative, you know, true positive, true ones, right? Ones that are detected as 1, correct values. 0, 0 here. Zeros that corrected as 0, that's correct. The others are, you know, 1 corrected as 0, sorry, detected as 0, and 0 detected as 1, the others. So basically, so again, true positive, you have an idea. Like true negative, also you have an idea, right? But what is false negative and false positive? So false negative is model incorrectly predicts negative. The model incorrectly predicts negative, meaning 0, right? When the actual value is positive, you know, so that's like missed detection. So it misses the 1. That's false negative. False positive, the other way around. So the model incorrectly predicts positive when the actual value is negative. That's false alarm. So for a medical test, right? If I want to give an example, false negative would be the test misses a sick patient, right? False positive would be the test like falsely classifies a healthy person as sick. So they're both bad. So Yeah, let's see how we find those values in our example. So again, let me see. Yes, so from import confusion matrix, yes, and assign that, I apply that to the y test. That's our actual values, and this is our predicted values. So let's see our confusion matrix. Excited? So 116 true positives, 41 true negatives. So this much, 157 out of 192 classified correctly. So that's good, right? That's not bad. And these are 35 of them classified wrong. Okay. So all right. We're gonna continue visualizing those, guys. Let's visualize this confusion matrix. Okay. And since there is like a lot of parameter options, I'll just copy paste from here that I run before. This will take some time. So, all right. And I'll explain over the code instead of just typing. All right. Now, we want to visualize again, our goal is to visualize the confusion matrix. Very easy. Don't get like, oh, what is this code? It's just using heat map, guys. You will see the output. I believe we already have, oh, we haven't. So we just import these libraries, the required libraries. Class names 0 and 1, right? 1 has diabetes, 0 does not have diabetes. And remember, subplots gives you two variable outputs, assign figure and axis. And you can basically class name 0, 1, you can create the tick marks, and then X would be and Y would be this way for the plot. And next thing, we're going to create the heat map. So that's come from the seaboard. And the data frame for this would be confusion matrix, as we said, right? Annotation true, that's giving the values for each cell. And this is the CMap that we've done already before. And label position on top. And then the title would be confusion matrix. Y label, the Y are actual labels, meaning they are the correct labels, like 1 or 0, right? And the X axis would be predicted. So when you run this, you will see now, just like you did see here, now you're gonna see this in heat map. Yeah, nothing crazy, just putting the confusion matrix in heat map using Seaborn. Okay, so there are a couple more concepts, but let's finish up here for today's lecture. So next we're gonna talk about, guys, some other metrics that derive from confusion metrics. So there's like 4 or 5 of them. Precision, recall, specificity, right? So recall is sensitivity. If you want to look at those terms before coming to the next course. Precision, recall, or sensitivity. Specificity, F1 score, and accuracy. So those 5 terms that we're gonna cover since we are talking about classification. So those are classification metrics. So again, what do we have? Precision, recall. This is also called sensitivity, guys. And the third one would be specificity. Some fancy terms, right? F1 score, accuracy. So there's gonna be a lot. So like a bunch of terms that we're gonna see. Will take time. So 2 more. 2 more. So those 5 plus we have something called ROC curve. So these are all evaluation metrics for classification. So we're gonna discuss these too. And AUC. So ROC is receiving operating characteristics curve. AUC, area under the curve. Okay, so before coming to the class, have a look at these metrics, what they mean, and they are all using confusion matrix terms like true positive, false negative, false positive, true negative. So we're gonna describe them, we're gonna define them, and do some more coding here, and then continue another concept in supervised learning.